Welcome to Orbit into Sleep. I'm so glad you found your way here tonight. Wherever you are right now, whether you're tucked beneath a warm duvet, lying in a quiet dark room, or just beginning to wind down after a long day, you are in exactly the right place. Tonight, we are leaving Earth behind. We are drifting upward, past the clouds, past the satellites, past the moon, and out into the vast, ancient beauty of our own galaxy, the Milky Way. Over the next little while, I'm going to share with you some of the most wonderful, most calming, most mind-expanding things we know about the galaxy we call home. Some of these discoveries are ancient. Some were made just last year. All of them, I think, will gently remind you just how extraordinary the universe is, and how small and safe and held we all are within it. There's nothing you need to do tonight, nowhere you need to be. Your only job right now is to breathe, to soften into wherever you're resting, and to let your mind float gently among the stars. Before we begin drifting off together, if you're enjoying what we do here at Orbit into Sleep, it would mean the world to us if you'd take just a moment to like this video and subscribe to the channel. It truly helps other restless minds find their way here and drift off just like you. We'd also love to hear from you in the comments. Let us know. Roughly how many hours of sleep do you usually get each night? We're curious and we read every single one. Now then, let's go somewhere beautiful. Drifting into the galaxy. Let's begin at the very beginning. Or rather, let's begin with a question so simple that it becomes, if you sit with it long enough, quite wonderful. What actually is the Milky Way? On a clear night far from city lights, you might look up and see a soft, faint smear of pale light stretching across the sky. It doesn't look like much at first. It's easy to overlook. But that gentle, hazy band of light is actually the combined glow of hundreds of billions of stars. You are looking edge on at the disk of the galaxy you live inside. The Milky Way is a barred spiral galaxy. Scientists give it a classification of SBBC, which is really just a precise way of saying it has graceful, sweeping spiral arms. And at its very center, a long bar-shaped structure made of stars, gas, and dust. Think of it a little like a cosmic pinwheel, slowly turning in the dark. Now, the fact that the Milky Way has a central bar wasn't always known. For a long time, we suspected it was a spiral, much like the nearby Andromeda galaxy, but the bar in the center was hidden. You see, the core of our galaxy is shrouded in thick clouds of interstellar dust and gas that absorb visible light, making it nearly impossible to see through with an ordinary telescope. It wasn't until astronomers turned to infrared and radio wave surveys, instruments that can pass through dust the way radio signals pass through walls, that the bar was finally confirmed. And that bar, it turns out, is a sign of maturity. Astronomers believe that bar structures in spiral galaxies form gradually over billions of years, through slow gravitational instabilities within the disk. A galaxy has to reach a certain age, a certain stability, before the stars naturally settle into that long central corridor. Our galaxy has reached that point. The Milky Way is, in a cosmic sense, fully grown. Now let's think for a moment about where home sits within all of this. Our solar system, the Sun, and its family of planets, including our own dear Earth, is not at the center of the Milky Way, not even close. We sit out toward the edges, about 27,000 light years from the galactic center. To picture that distance, 1 light year is roughly 6 trillion miles, 27,000 of those. We are very much in the suburbs. Our address, more specifically, is on the inner edge of something called the Orion Arm. The Milky Way has 4 major spiral arms, broad sweeping rivers of stars and gas, named Perseus, Scutum Centaurus, Sagittarius, and Norma. The Orion Arm is a smaller segment nestled between them, and it is home. There's something rather lovely about that, isn't there? To know that you have a cosmic address, that on some unimaginable scale, right now, your small, warm body is tucked into a minor arm of a barred spiral galaxy, drifting slowly through the dark. The Sun, carrying all of us along with it, takes about 240 million years to complete 1 full orbit around the center of the Milky Way. 1 orbit. Astronomers call this a galactic year. The last time the Sun was in this same position along its path, the Triassic period was just beginning on Earth, and the very first dinosaurs were taking their first steps. And before that? In the previous galactic year, there were no complex animals at all. The oceans were full of strange, soft creatures we'd barely recognize. 1 slow orbit, 240 million years, and we haven't even finished one. Let your mind sit with that for a moment. Let it expand outward. There's no hurry. You have all night. The disk of the Milky Way is vast. Measured across, it stretches roughly 87,000 light years from one edge to the other, and yet, compared to its width, it is remarkably thin. The part of the disk where most of the young stars and gas clouds live, the thin disk, is only about 1,000 light years deep. That's paper thin on a galactic scale. A flat, spinning plate of stars and dust, slowly turning in the void. Around that thin disk sits a slightly thicker layer, called simply the thick disk. It's about 3,000 light years deep and contains older, more settled stars that formed long ago. And here's something that surprised astronomers quite recently. When they analyzed data from the Gaia space mission, the most precise map of stars ever created, they found that this thick disk began forming around 13 billion years ago. That is only about 800 million years after the Big Bang itself. Our galaxy's structure was taking shape almost as soon as the universe cooled enough to allow it. The universe is approximately 13.8 billion years old. The Milky Way's thick disk started forming just 800 million years into that story. In cosmic terms, we are an ancient place. And yet, for most of human history, we had no idea. As recently as a few centuries ago, the pale band of the Milky Way was a mystery. Ancient Greek philosophers looked up at it and argued about what it could possibly be. The great philosopher Aristotle believed it was a meteorological phenomenon, something happening in the upper celestial weather, he placed it firmly in the earthly realm, not the heavenly one. It was Democritus, the atomist philosopher, who came closest to the truth. He suggested, rather beautifully, that the Milky Band might be made of distant stars, too numerous and far away to see individually. He was right, but it would take nearly 2,000 years for anyone to prove it. That proof came on a winter night in January 1610, when a man in Padua turned a newly improved telescope toward that pale smear in the sky. His name was Galileo Galilei, and what he saw astonished him. The soft glow resolved into thousands, tens of thousands of individual stars, countless pinpoints of light packed so densely together that from Earth they merged into a single band of luminescence. The Milky Way was not a cloud, it was not weather, it was stars, vast, incomprehensible numbers of stars. That moment, just over 400 years ago, changed everything. After Galileo, the question became not what the Milky Way was, but how big it was. And answering that question would take another 300 years, a series of brilliant minds, at least one famous public debate, and the discovery of a very special kind of star. Let's drift there now. By the late 1700s, a German-born astronomer living in England, William Herschel, along with his remarkable sister Caroline, set out to map the galaxy by counting stars. They called their method star gauges. Night after night, they pointed their telescope in hundreds of directions across the sky and simply counted how many stars they could see in each direction. More stars in a direction, they reasoned, meant the galaxy extended further that way. Fewer stars meant they were looking toward an edge. Their conclusion was that the stars were arranged in a great flat system, a grindstone shape, just as Thomas Wright had proposed in 1750, and they placed the sun right at the center of it all. They were right about the shape, they were wrong about our position. The error was understandable. They didn't know about interstellar dust. Those vast clouds of gas and dust that fill the galaxy don't just hide things from view. They absorb starlight, making distant stars appear dimmer and more scarce than they truly are. So when the Herschels looked in the direction of the galactic center, the dust made it seem as though the stars thinned out there, just as they appeared to thin out in all other directions. The sun looked central simply because they could not see far enough in any direction to notice otherwise. This misunderstanding persisted for over 100 years. The correction came from an astronomer named Harlow Shapley in the early 20th century. He wasn't studying the disk of stars directly. He was studying globular clusters, these gorgeous, tightly packed spheres of ancient stars that orbit the Milky Way like a swarm of satellites. Shapley noticed something crucial. These clusters were not evenly distributed around the sky. They were concentrated toward one particular region, toward the constellation Sagittarius. If the sun were truly at the center, the clusters should be spread evenly around us. The fact that they were clustered in one direction told Shapley something remarkable. The center of the galaxy was not where we were. The center was over there, in Sagittarius, tens of thousands of light years away. We were not at the middle of things. We were drifting in the outer districts, looking in. Take a slow breath, let that settle. There is something deeply calming about not being the center, about being one small, warm point among hundreds of billions, carried gently along in a slow galactic orbit with no particular destination and no particular rush. You don't have to be the center of anything tonight. You can just float. The heart of darkness and the stars that dance around it. If you were to travel from here to the center of the Milky Way, across those 27,000 light years of stars, gas, and dust, you would eventually arrive at a region of extraordinary density. The stars here are packed thousands of times more tightly than in our quiet neighborhood. Space grows loud with radiation and magnetic fields. And right at the very heart of it all, hidden but immense, sits something almost incomprehensible, a supermassive black hole. Its name is Sagittarius A star, or S-star A star for short, and it has a mass of approximately 4.3 million times that of our Sun, all compressed into a region no larger than the distance from the Sun to the planet Uranus. 17 light hours across, that's the rough space within which more than 4 million suns worth of mass is contained. It was first detected in 1974 by two radio astronomers, Bruce Balick and Robert Brown, who noticed a compact, bright radio source sitting exactly at the geometric center of the galaxy. At the time, they couldn't be entirely sure what it was, but the signal was too concentrated, too precise to be anything ordinary. Confirming the true nature of Sagittarius A star took decades of patient watching, and the proof came from something remarkable: stars. Near the center of the galaxy, a group of stars orbit Sagittarius A star at extraordinary speeds. These are known as the S stars, and astronomers have been tracking them since the 1990s. One of these, a star called S2, completes a full orbit around the black hole every 16 years. To do so, it reaches speeds of up to 7,700 kilometers per second at its closest approach. That is roughly 2.6% of the speed of light. Think about that for a moment. 2.6% of the speed of light. That star is moving so fast that if it could somehow travel across the Earth, it would cross the entire diameter of our planet in less than the blink of an eye. And S2 is not even the fastest. Another star, S4714, has been clocked at nearly 24,000 kilometers per second at its closest pass. That is 8% of the speed of light. Our galaxy has stars that move at 8% the speed of light, trapped in tight, swooping orbits around an invisible point of gravity at the center of everything. By watching these stars trace their paths, astronomers could calculate the precise mass of the object pulling at them. And there was simply no explanation other than a black hole, a single point, or something close to it, containing more than 4 million solar masses, bending space and time, and pulling those stars into their tight, frantic ellipses. Then in 2022, something extraordinary happened. The Event Horizon Telescope, a network of radio telescopes spread across the entire surface of the Earth, working together as one enormous instrument, captured the first ever direct image of Sagittarius A star. Not just a signal, an image, a glowing ring of superheated gas surrounding a dark shadow at the center, the shadow of the black hole itself. For the first time in human history, we could see the heart of our galaxy. It was not a dramatic blazing fire. It was a quiet ring, a soft glow around an absence, beautiful in its restraint. Now, Sagittarius A star is not dormant, far from it. Recent observations by the James Webb Space Telescope have revealed that it flares constantly, a never-ending stream of activity ranging from faint flickers lasting just seconds to bright surges that erupt every day. These flares are caused by magnetic reconnection events, moments when magnetic field lines in the swirling gas around the black hole collide, reconfigure, and release enormous bursts of energy in the form of particles moving close to the speed of light. In 2013 and 2014, the Chandra X-ray Observatory caught Sagittarius A star, producing what astronomers called mega flares, bursts of X-ray light 400 and 200 times brighter than its usual output. And in April 2024, a combination of Webb, the New Star Telescope, and the Very Large Array detected a strong X-ray flare, followed by a brightening in radio waves about an hour later. The delay is thought to be caused by a magnetic flux rope, a tube of tangled magnetic energy being ejected from the inner regions of the black hole's accretion disk, expanding and cooling as it moves outward. The black hole at the center of our galaxy is busy. It is magnetic. It is alive with energy. And yet, from here, 27,000 light years away, we feel nothing. We are safe in our quiet suburban spiral arm, carried in gentle orbit, entirely unaware of the drama at the center. Sometimes the most turbulent things are the most distant, and distance is a kind of peace. Above and below the center of the galaxy, something else was discovered in 2010 that stopped astronomers in their tracks. The Fermi Gamma Ray Space Telescope revealed two enormous bubble-like structures extending 25,000 light years above and below the galactic plane, one in each direction, symmetrical and vast. They were later shown to have well-defined sharp edges, and they glowed with high-energy gamma radiation. These became known as the Fermi bubbles. Nobody expected them. Nothing in the existing models of the galaxy predicted structures quite like this. They are bigger than most galaxies. They have been sitting there, blossoming silently above and below the heart of the Milky Way for millions of years. What caused them is still debated. One theory says that millions of years ago, Sagittarius A star consumed a vast amount of material, equivalent to the mass of 10,000 suns, in a relatively short time. The energy released from that feast launched jets of radiation and particles outward, inflating the bubbles like two enormous balloons expanding into the halo. The total energy involved in this event is estimated to have been immense, far beyond anything we could meaningfully picture. The other theory suggests the bubbles were inflated not by the black hole, but by an intense burst of star formation at the galactic center. Thousands of massive stars forming, burning bright, and then exploding as supernovae over tens of millions of years, their combined winds and shock waves gradually driving material outward into the halo. Both theories have their supporters. Both are extraordinary. In 2020, the Rosetta telescope found even larger X-ray bubbles surrounding the Fermi structures. So the bubbles have layers. A gamma-ray core within a larger X-ray shell, all of it stretching for tens of thousands of light years in both directions. Our galaxy is breathing, slowly, enormously breathing. Then, in 2025, astronomers found something smaller but equally telling. A young star cluster called Westerlund 1, much closer and more modest in scale, is producing its own nascent bubble of gamma rays, extending about 650 light years below the galactic plane. It is, in miniature, the same process. Stellar winds and supernovae from a cluster of massive young stars, driving a bubble of energetic particles outward. We are watching the galaxy build itself, layer by layer, outflow by outflow, bubble by bubble. And in the quiet of your room, on this small planet in a minor spiral arm, you are part of it. The atoms in your body were forged in the hearts of stars, carried across interstellar space in exactly these kinds of outflows. You are, in the most literal sense, made of the galaxy. That thought is worth sitting with as your breathing slows and your body grows heavy and your mind begins to wander. You are made of the Milky Way. And the Milky Way is dreaming tonight, the ancient bones of the galaxy. The Milky Way is not a simple or static thing. It is old in the way that only the universe can be old, measured in billions of years, built layer by layer, shaped by collisions and mergers and ancient catastrophes that happened before our sun even existed. Scientists who study this deep history call themselves galactic archaeologists, and rather like archaeologists who sift through soil to find the remains of lost civilizations, these astronomers sift through the chemical compositions and orbital patterns of stars to find the remains of galaxies that were swallowed by our own billions of years ago. Because the Milky Way, it turns out, has been eating, stars hold their history in their chemistry. When a star is born, it carries within it the chemical fingerprint of the gas cloud it formed from. That fingerprint, the proportions of iron, oxygen, silicon, and hundreds of other elements never changes. So when astronomers measure the chemistry of ancient stars today, they can trace those stars back to their original environments, even if those environments were galaxies that were destroyed and absorbed long before Earth existed. The single most transformative event in the Milky Way's history that we know of is called the Gaia-Enceladus merger, also nicknamed the Sausage Galaxy, and it happened somewhere between 8 and 11 billion years ago. At that time, a substantial dwarf galaxy, carrying roughly 50 billion solar masses of stars, gas, dark matter, and globular clusters, fell into the young Milky Way. The collision was not a gentle brushing, it was a deep, plunging merger. The incoming galaxy struck the Milky Way's disk nearly head-on, and the impact was enormous. The energy of that collision puffed up the pre-existing thin disk of the Milky Way, thickening it and disrupting it. It triggered a burst of new star formation as gas was compressed and heated, and it added at least 8 globular clusters, those beautiful ancient spheres of densely packed stars, to our galaxy's collection. The stars from that ancient merged galaxy are still here. They move among us now, interspersed throughout the inner halo, but on distinctively different orbits. Their paths are eccentric and elongated, stretched out like long, flattened ellipses rather than the more circular orbits of stars born in the Milky Way itself. And their chemistry marks them as foreign-born. When you look at a star in the halo with an unusual orbit and an unusual chemical signature, you may be looking at something that formed in a different galaxy entirely, absorbed into ours billions of years before life appeared on Earth. The thick disk, the one that began forming 13 billion years ago, was shaped in part by that ancient collision. The disruption created it, in a sense. The sausage galaxy gave us one of our own structural layers. More recently, on a galactic timescale, another dwarf galaxy has been making its presence felt. The Sagittarius dwarf elliptical galaxy has passed through the Milky Way's disk not once, but 3 times over the last 4 to 5 billion years. Each pass sends ripples through the disk the way a stone dropped in still water sends out rings. The disk rings and wobbles and oscillates. The whole galaxy, vast as it is, responds. These passages have been consequential. They have driven waves of star formation. They have altered the chemical evolution of the disk, specifically increasing the abundance of oxygen in the last 4 billion years. And here is something astonishing. Recent analysis of Gaia data suggests that one of these passages by the Sagittarius dwarf may have been the very trigger that caused the gas cloud to collapse that formed our own sun, and with it, the Earth, and eventually us. We may owe our existence to a dwarf galaxy that is currently being torn apart by our own. The Sagittarius dwarf has left long, flowing streams of stars arcing over the galactic poles, trails of stellar debris called Sagittarius streams, visible to astronomers as curved lines of stars that had been pulled free from the dwarf and flung across the sky. They are beautiful and melancholy, the remnants of a galaxy that once existed independently and now survives only as threads woven through the halo of a larger one. Our galaxy is not finished eating. The Sagittarius dwarf is still being absorbed. The Large Magellanic Cloud and the Small Magellanic Cloud, those 2 bright companion galaxies visible from the southern hemisphere, are also in the very long run headed toward absorption. They orbit us. They trail behind them their own stream of gas called the Magellanic Stream, which extends over 100 degrees across the sky. And over billions of years, their orbits will decay, and they too will be drawn in. This is how galaxies grow. not in sudden dramatic explosions, but in long, slow, gravitational embraces. One galaxy drifting toward another, an orbit that decays, an infall, a merger, and all of it taking so long that from inside one of the galaxies nothing seems to be happening at all. Now, at the very center of all this ancient history, in the innermost few thousand light years of the galaxy, there is a region astronomers have recently named the Poor Old Heart. It is exactly what it sounds like, a concentration of the galaxy's oldest, most ancient stars, formed in the very first billion years of the universe's existence. These stars are chemically primitive, made almost entirely of hydrogen and helium, with very little of the heavier elements that later generations of stars would create and disperse. Within this poor old heart, in 2024, researchers identified two distinct ancient structures, which they named Shakti and Shiva. Each contains around 10 million solar masses of stars, all moving in similar orbits with nearly identical chemical profiles. They are, as best as astronomers can determine, the very first building blocks of what would become the Milky Way, the first pieces of the proto-galaxy, assembled 12 to 13 billion years ago. Shakti and Shiva, named for ancient cosmic forces, the builders of what came after. There is something deeply moving about that, I think. The galaxy has a heart, and its heart is old and quiet and has been there almost since the beginning of time. As you lie there in the dark, feeling the warmth of your blanket, the quiet of the room around you, let your mind move gently backward through time, past the dinosaurs, past the formation of the earth, past the birth of the sun, back through 8 billion years of galactic mergers and star formation and slow orbital dances, all the way to the very beginning when Shakti and Shiva first gathered themselves together in the dark and the galaxy was just starting to breathe. Everything since then has been a long, slow, extraordinary story, and you are, improbably and wonderfully, part of it. If you're finding it hard to fall asleep, we've put together some resources in the description below that we think might help. Take a look when you get a chance. No pressure at all, just some gentle options we've found helpful. We hope something there is useful to you. Neighbors in the dark and the mystery of the missing galaxies. Our galaxy does not drift alone. The Milky Way exists within a gravitationally bound collection of galaxies called the local group. There are more than 134 known members, and the vast majority of them are small dwarf galaxies, quiet and dim, orbiting the two dominant giants, us and the Andromeda galaxy. The local group stretches across roughly 16.7 million light-years from one end to the other, a vast but self-contained neighborhood of the universe. Its center of mass, the gravitational midpoint that the whole system rotates around, sits about 1.46 million light-years away from us, slightly closer to Andromeda, which may actually be the more massive of the two, though astronomers continue to refine the measurements. Beyond the local group, things scale up rapidly. We are part of a larger flattened region called the local sheet, about 17 million light-years across. That itself is nested within the Virgo supercluster, which is a part of the enormous Laniakea supercluster. a vast cosmic structure containing thousands of galaxies arranged like the branches of a tree, all flowing slowly toward a gravitational attractor. We are small, but we are not alone. We are connected to everything. Now, within our local group and its surroundings, there are some mysteries that have puzzled astronomers for a long time. One of them involves a number that doesn't quite add up. Standard cosmological models, the best theoretical frameworks we have for understanding how the universe is structured and how galaxies form, predict that the Milky Way should be surrounded by hundreds of satellite galaxies, smaller galaxies in orbit around our own. The models are clear about this. There should be hundreds, but we've only confirmed around 60. Where are the rest? In 2025, supercomputer simulations at Durham University offered a possible answer. These simulations suggested that there are likely 80 to 100 additional satellite galaxies orbiting nearby, but they are essentially invisible to current telescopes. They have been stripped of their dark matter and their gas by the gravitational forces of the Milky Way over billions of years. Without dark matter to hold them together and without gas to form new stars, these remnant galaxies have faded to almost nothing. Astronomers are calling them ghost galaxies or orphan galaxies. They are there. We just cannot see them yet. Future telescopes, in particular the Vera C. Rubin Observatory, which is designed to survey the southern sky with extraordinary sensitivity, may be able to detect the faint stellar halos of these ghost systems. Finding them would be remarkable because it would confirm that our theoretical models are basically right, that the missing galaxies were always there, just rendered invisible by time and tidal stripping. The universe, it turns out, is full of things we know must be there but cannot yet see. Speaking of things we cannot see, let us talk for a moment about dark matter. Because when it comes to the Milky Way, dark matter is everywhere, or rather, everywhere and nowhere, present in enormous quantity, but invisible to every instrument we have except for its gravitational effects. In a galaxy where mass is spread in a normal, visible way, the stars at the outer edges should orbit more slowly than the stars closer to the center. This is the same principle that makes the outer planets in our solar system travel more slowly than the inner ones. Less mass enclosed within your orbit means less gravitational pull, which means lower speed. In the 1970s, astronomer Vera Rubin made careful measurements of the rotation speeds of spiral galaxies and found something that contradicted all expectations. The stars at the outer edges of galaxies were not slowing down. They were moving just as fast as stars closer to the center, or in some cases even faster. The rotation curve, the graph of speed against distance from the center, was flat. The only explanation that worked was invisible mass. Vast amounts of it distributed in a great sphere around the visible disk, extending far beyond the edge of the stars. Mass that did not emit or reflect light, did not interact electromagnetically, but exerted gravity, dark matter. For the Milky Way, it is currently estimated that roughly 90 to 95% of all its mass is dark matter. The hundreds of billions of visible stars, all that glittering light, represents only about 5% of what's actually there. The rest is dark, a vast, invisible cocoon surrounding everything we can see. And yet, something fascinating emerged from the most recent data. Measurements from the Gaia mission and other surveys have found that at the extreme outer edges of the Milky Way, beyond the visible disk, the rotation curve is not flat. It drops. Stars out there are moving slower than expected. This decline is called a Keplerian drop, and it suggests that the dark matter halo surrounding our galaxy may be lighter and less dense than models have assumed. The Milky Way may be 4 to 5 times lighter than previously thought. This is not settled science. The measurements are being tested and refined. But it is a significant challenge to the existing picture. If the dark matter halo is smaller and less dense, that changes nearly everything downstream: the probability of mergers, the behavior of satellite galaxies, the long-term fate of the Milky Way itself. Science, beautiful and rigorous as it is always in motion. What we know today may be refined tomorrow. The galaxy is always ahead of us, always a little more complex than our models expect. There is something reassuring about that, I think. The universe is not a closed book. It is still being written. And we are, in our small way, part of the story it is telling about itself. Now, in 2026, a discovery was announced that added another layer to our understanding of the local universe. Researchers identified what has been called a giant cosmic sheet surrounding the local group. It is a vast, flat structure of dark matter and ordinary matter, extending around the neighborhood of galaxies we inhabit. This structure appears to be responsible for something strange that had puzzled astronomers for some time. The fact that several nearby galaxies seem to be speeding away from the Milky Way faster than gravity alone would predict, as if being pushed outward. The giant cosmic sheet appears to create a kind of local pressure, a dark matter-dominated shell that drives this expansion. What seemed like an anomaly turns out to have a structure. What looked like chaos has a shape. The universe is always finding ways to organize itself, even on scales so vast they are difficult to think about without losing one's footing entirely. And so let the thought of that vast sheet curving around our entire local cluster of galaxies, drifting slowly through the dark, be a kind of comfort. We are held within something, surrounded on all sides by structure, by the invisible geometry of space and matter and dark matter. We are not lost in a void. We are nested within something ancient and immense. Let your breathing slow now. Let your thoughts drift outward, past the local group, past the local sheet, into the great dark web of the universe. There is no need to hold anything right now. No need to stay awake to keep watch. The galaxy will carry you through the night. The long question of what comes next. For most of a century, the future of the Milky Way seemed settled, inevitable even. The Andromeda galaxy, our nearest large neighbor, is moving toward us. It has been moving toward us for a very long time, approaching at around 250,000 miles per hour, and astronomers, running the numbers, concluded that in approximately 4 to 5 billion years, the two galaxies would collide. The collision, they said, would be enormous and slow and magnificent. Over billions of years, the spiral arms would pass through each other. The gravitational disturbances would fling stars into new orbits. The neat spiral structures of both galaxies would be gradually destroyed, and the two systems would merge into a single large elliptical galaxy. Some have called this future galaxy Milkomeda. It seemed certain. Then, in 2025, a team of researchers led by Til Sawala published a study in the journal Nature Astronomy that changed the picture considerably. Using updated data from Gaia and Hubble and running 100,000 separate simulations of how the local group might evolve, they found something surprising. The probability of a full merger between the Milky Way and Andromeda within the next 10 billion years is only about 50%, a coin flip. The reason for this new uncertainty comes from two sources. First, the Large Magellanic Cloud. This companion galaxy, visible from the southern hemisphere as a bright smear of light near the Milky Way, turns out to be much more massive than previously thought, roughly 10% of the Milky Way's own mass. Its gravitational pull is actively tugging the Milky Way slightly off its original trajectory. It's nudging us, and that nudge, accumulated over billions of years, could be enough to cause the Milky Way to miss Andromeda entirely, or at least to change the geometry of the encounter significantly. Second, the Triangulum Galaxy, M33, Andromeda's largest satellite, also has an influence. Its mass and its orbital path add additional variables to the prediction, and with enough variables, certainty dissolves into probability, so it may happen, or it may not. The galaxies may brush past each other, exchanging stars and gravitational disturbances without ever fully merging, or they may miss each other almost entirely. We are living in a universe of genuine uncertainty about our own cosmic future. If the collision does occur, it is worth knowing that the experience from the inside would not be dramatic in the way you might imagine. Stars, despite appearing clustered and close together from a great distance, are separated by enormous voids. In our neighborhood, stars are typically several light years apart. The chance of any two individual stars actually colliding during a galactic merger is astronomically small. Instead, the merger would reshape orbits. Stars would be flung into new paths. The elegant spirals would unravel, and over hundreds of millions of years, the merged system would slowly settle into a new shape. The night sky would look different, of course, much more crowded and complex. The faint band of the Milky Way, as we know it, would gradually be replaced by something stranger and more luminous as two galaxies worth of stars redistributed themselves across the sky. But life on Earth, if it still existed, would not end due to the merger. The physical danger to any individual solar system from another star passing close would be vanishingly small, though there is, of course, another factor. The sun is not static. It is slowly growing brighter as it ages. In approximately 1 to 1.5 billion years, The sun's increasing luminosity will heat the Earth's surface enough to boil away the oceans. Long before any galactic collision could occur, Earth as a habitable world will have ended. Whatever story humanity or its descendants are telling at that point will have moved elsewhere, if it is being told at all. This is not a gloomy thought, or it does not have to be. 1 to 1.5 billion years is so incomprehensibly long that it exists purely as an abstraction. The universe has been around for only about 13 times that duration. Everything we know, all of recorded history, all of human civilization, all of the evolution of complex life on Earth, represents a tiny fraction of even that 1 billion years. We are very, very early. The universe is young, or at least it is not old, and there is enormous time stretching ahead, enormous space to explore, enormous stories still to unfold. And right now, in this moment, you are here, small and warm and alive and breathing slowly in the dark, on a planet circling a middling star in a quiet arm of a barred spiral galaxy that has been slowly turning for 13 billion years. There is nothing you need to do about any of this. You don't need to hold the galaxy together or solve the dark matter problem or figure out whether Andromeda will arrive. You don't need to understand quantum field theory or the formation of globular clusters or the retrograde precession of the galactic warp. You just need to rest. The galaxy is turning without your help. The stars are burning without your attention. The dark matter is curving space around the halo of the Milky Way right now, as it has been doing since long before anyone was there to know about it. Everything is unfolding exactly as it should. Your body knows how to sleep. It has been doing it for your entire life, and for millions of years before that. Long before you were born. The rhythm is already in you. The stillness is already there, just beneath the surface. Let the music carry you now. Let your mind wander where it would like to go. Through the spiral arms, past the Fermi bubbles, out into the halo where the ancient stars of Gaia and Enceladus drift in their long, eccentric orbits, into the poor old heart where Shakti and Shiva still remember the earliest days, out to the edge of the local group and beyond, into the giant cosmic sheet, and further still. There is no limit to where a dreaming mind can go. You have the whole galaxy tonight, all of it. Every star, every cloud of gas, every invisible thread of dark matter, every ancient merger and newborn nebula and slowly precessing warp. It is all yours. Rest well, you have earned it.